Apex 2012 introduces several new features that are enabled prior to ray trace. Those features are listed in the ray trace settings window as shown here. The ray path analysis automatically computes and displays ray paths. Ray fluence and absorbed analysis computes energy density and absorbed energy and outputs that data in a numerical format. Ray critical surface analysis is commonly used in stray light analysis to help to determine the first-order paths of an optical system. Let's start here and take a look at the critical surface analysis in detail. The first thing I need to remember to do is to check Identify Critical Surfaces before the ray trace. Down below we have two options, Directly Seen and Indirectly Seen. Directly seen refers to surfaces that are seen by the detector, possibly through lenses and mirrors. Indirectly seen surfaces are those seen by the detector via ghost reflections off from the lens surfaces. For this analysis, we'll just use the default, directly seen, and click OK. In this case, we'll demonstrate this feature using a Cassegrain telescope. As we can see over here in the Optics Manager tree, I've turned the detector into an emitting surface. Using the Select option, I've restricted the cone angle of the rays to illuminate the back port of the telescope system. Let's do a ray trace and see which surfaces are reported as critical. On the left side of the split screen interface shown below, we have a listing of our directly seen surfaces. Each row contains the number of rays that landed on that surface, the total flux associated with those rays, and the surface name. By clicking on the different rows here, we can confirm the location of that particular object in the graphic pane. By clicking on the Set Scatter Model button here, the user can optionally apply scatter properties to that surface. Now that we've seen what the critical surface analysis looks like, let's take a look at the new ray path feature. For this demonstration, we'll use an optical system that's suitable for a ghost analysis. The first step is to go back to the Trace menu and bring up the Trace Settings dialog box, select Ray Path Analysis, and tell the program to save the ray path analysis data. Then we just close this window by clicking on OK, and then select Trace Rays. To display the path data at the detector, I come down here in the Optics Manager tree, highlight the detector, then go to the Analyze menu and click on the Path Data button. We'll just use the defaults, which is to list all of the paths at the detector. The second option here, Filter Paths By, allows the user to filter out some of the paths based on their flux threshold or a minimum ray count. We'll select OK. And here we see the path data. Looking at the columns here, we have path number, the number of rays associated with each of those paths, the total flux associated with those rays, the percent contribution of the total, the number of surfaces hit, and additional information which includes data about how the ray got to the detector. By selecting the different rows in this table, we can toggle on and off that particular path in the graphic pane view. Also, you'll notice that on the right side of the screen, we get more detailed information about that particular ray path. In this particular case, if we scroll down, we see that these rays have been reported as splitting at surfaces 6 and 9. If we're not sure what those surfaces are, we can check the highlight box here, and the surfaces are highlighted in the graphic pane. The user also has the option of displaying just every nth ray, or use the only option to set the absolute number of rays that are displayed. And there are a couple additional options that are available that can be seen by expanding the split view interface. Using the color option, the user can customize the color for the various ray trace paths. For instance, here, I'll select red. Finally, the overlay option can be used to display several ray paths at the same time. And that's a quick overview of the new analysis features in Apex 2012. The ray path and critical surface analysis options are particularly useful for doing efficient stray light analysis.